Welcome back to Operating Systems Crashcast. I'm Victor, and today we're diving into Section 6.7, Operating System Examples. We'll be exploring how different operating systems implement CPU scheduling in the real world. Sheila, are you ready to take our listeners on this journey through practical OS scheduling?
Absolutely, Victor. I'm excited to see how the scheduling algorithms we've discussed in previous episodes are put into practice by major operating systems. It's always fascinating to see theory applied in real-world scenarios.
Great point, Sheila. Before we jump into specific examples, let's quickly recap the basics of CPU scheduling. We've learned that scheduling is crucial for multitasking operating systems to manage processor time efficiently. The goal is to keep the CPU busy and ensure fair allocation of resources among processes.
Exactly, Victor. And we've covered various scheduling algorithms like first come, first served, FCFS, shortest job first, SJF, priority scheduling, and round robin. Now let's see how these concepts are implemented in some popular operating systems, starting with Windows.
Windows uses a priority-based preemptive scheduling algorithm. It has 32 priority levels, divided into two classes, real-time, 16, 31, and variable, 0, 15. The Windows scheduler ensures that the highest priority ready thread always runs.
That's interesting, Victor. How does Windows handle threads with the same priority level?
Great question. Windows uses a round-robin algorithm for threads with the same priority. Each thread gets a time quantum, which is a fixed amount of CPU time, typically around 20 milliseconds. If a thread doesn't complete within its quantum, it's preempted and moved to the end of the queue for its priority level.
I see. So Windows combines priority scheduling with round robin. Now, let's move on to Linux. How does its scheduling differ from Windows?
Linux uses the Completely Fair Scheduler, CFS, for normal processes. Unlike Windows' fixed time quantum, CFS aims to give each process a fair share of CPU time based on the number of runnable processes. It uses a red-black tree data structure to efficiently manage processes.
That sounds quite different from Windows. Does Linux have any special considerations for real-time processes?
Indeed it does, Sheila. Linux has a separate scheduler for real-time tasks, which uses a priority-based system similar to Windows. Real-time tasks always have higher priority than normal tasks managed by CFS.
Fascinating. Now let's talk about Solaris. How does its approach to scheduling compare to Windows and Linux?
Solaris uses a multi-level feedback queue with priority classes. It has a unique feature called Fair Share Scheduler, FSS, that allocates CPU time not just to processes, but to groups of processes or users. This allows for more fine-grained control over resource allocation.
That's an interesting approach. It seems like each operating system has its own unique take on scheduling. What are some key takeaways from these examples that our listeners should remember, especially for interviews?
Great question, Sheila. First, it's important to note that real-world operating systems often combine multiple scheduling algorithms to balance different needs. Windows prioritizes real-time tasks while using round-robin for equal priority threads. Linux emphasizes fairness for normal tasks while having a separate system for real-time processes. Solaris introduces the concept of fair sharing among groups.
Those are excellent points, Victor. It's also worth mentioning that these scheduling approaches reflect the primary use cases of each OS. Windows, being commonly used in desktop environments, needs to balance responsiveness with fairness. Linux, often used in server environments, focuses on overall fairness and efficiency. Solaris, with its roots in enterprise systems, provides fine-grained control over resource allocation.
Absolutely right, Sheila. Another key takeaway is the trade-offs involved in these scheduling decisions. For example, Windows' fixed time quantum provides predictable behavior, but might not be as efficient as Linux's variable approach in all situations. On the other hand, Linux's CFS might provide better overall throughput, but could potentially lead to less predictable response times for individual processes.
That's a crucial point about trade-offs, Victor. It reminds us that there's no one-size-fits-all solution in operating system design. Each approach has its strengths and weaknesses, and the choice depends on the specific requirements and use cases of the system.
Exactly, Sheila. As we wrap up, let's quickly recap the key points we've covered. We've seen how Windows uses a priority-based preemptive scheduler with round-robin for equal priority threads. Linux employs the completely fair scheduler for normal tasks and a separate scheduler for real-time processes. Solaris introduces the concept of fair share scheduling among groups of processes or users.
Great summary, Victor. We've also highlighted the importance of understanding the trade-offs in different scheduling approaches and how they relate to the primary use cases of each operating system. This knowledge is crucial for anyone working with or designing operating systems.
Absolutely, Sheila. That brings us to the end of today's episode on operating system examples for CPU scheduling. Thanks to all our listeners for tuning in. Remember, understanding these real-world implementations can give you valuable insights into operating system design and performance. Until next time, keep exploring the fascinating world of operating systems.